Hello there, and welcome to Space Historians. I'm so glad you found your way here tonight. Before we begin our journey into one of the most mysterious regions of the cosmos, take a moment to get comfortable. Adjust your pillow, let your body settle into whatever position feels most natural, and know that there's nowhere else you need to be for the next couple of hours. Where in the world are you watching from? A quiet bedroom where the day has finally released its hold? A cozy corner where you've retreated from the noise and light? Wherever you are, you're welcome here. Tonight we're going to explore something called the Boötes Void, sometimes known as the Great Nothing. It's a region of space so vast and so empty that when astronomers first discovered it, they could barely believe what they were seeing. We'll discover how this cosmic void was found, understand what it means for our understanding of the universe's structure, and contemplate what might exist in that extraordinary darkness. It's a journey that spans hundreds of millions of light years and touches on some of the deepest questions about the nature of reality itself. But don't worry. This isn't going to be a frantic race through alarming cosmic phenomena or a breathless catalogue of space horrors. Instead, we'll move slowly and carefully through the science, the discovery, and the implications of this remarkable void, taking our time with each revelation. We'll approach this mystery the way astronomers themselves have approached it, with patience, curiosity, and a sense of profound wonder. By the end, I think you'll find that even in the darkest, emptiest regions of space, there's beauty worth contemplating. If you enjoy these calm explorations of the cosmos, a like and subscribe really helps reach others seeking the same peaceful way to end their day. And to those already subscribed, thank you for being here, for trusting these journeys into the night sky. So settle in, let your shoulders drop away from your ears, take a slow breath, and as you exhale, let the tension of the day drain away. And let's begin our slow drift into the Boötes Void, into that magnificent emptiness between the stars. There's nowhere you need to be right now. Nothing you need to solve or fix or remember. Just listen, and let the story unfold like the universe itself, vast and patient and infinitely gentle. Before we can truly understand what makes the Boötes Void so remarkable, we need to step back and look at how the universe organizes itself on the larger scales. Picture, if you will, the entire observable universe. That sphere of space roughly 93 billion light-years across that represents everything we can possibly see from Earth. Now imagine that you could somehow pull back far enough to see the distribution of all the galaxies, all the matter, all the light in that incomprehensible volume. What would you see? You might expect a relatively even distribution. Galaxies scattered more or less randomly, like salt sprinkled on a dark table. But the universe has other ideas. When cosmologists map the large-scale structure of the cosmos, what emerges is something far more intricate and beautiful than random distribution. The universe organizes itself into what scientists call the cosmic web, a vast three-dimensional tapestry of matter and light that stretches across billions of light years. This cosmic web consists of several distinct components, each playing a role in the grand architecture of everything that exists. First, there are the galaxy clusters, dense congregations where hundreds or even thousands of galaxies gather together, bound by gravity into enormous structures. These clusters are bright, busy places in cosmic terms, full of galaxies interacting, merging and forming new stars. Then there are the filaments, long strands of galaxies and dark matter that connect the clusters like bridges spanning cosmic canyons. These filaments can stretch for hundreds of millions of light years, creating the threads that give the cosmic web its name. Between the filaments you find something else entirely. These are the voids, vast regions where galaxies are few and far between, where the density of matter drops to a tiny fraction of the cosmic average. And it's here, in these quiet, dark places, that our story truly begins. Because while voids are a natural part of the cosmic web structure, some voids are so large, so empty, that they challenge our understanding of how the universe came to be organised this way. The cosmic web isn't random. It emerged from tiny fluctuations in the density of matter in the very early universe, moments after the Big Bang. Where matter was slightly more dense, gravity pulled more matter in, creating the seeds of galaxy clusters. Where matter was slightly less dense, it was pulled away toward denser regions, creating voids that grew larger over billions of years. This process, called gravitational instability, has been sculpting the universe's structure for more than 13 billion years, creating the magnificent web we observe today. What's fascinating is that we can see this structure because of light, because galaxies shine. Where galaxies cluster together, we see brightness. Where they're absent, we see darkness. And in 1981, an astronomer looking at a survey of galaxy positions noticed something that shouldn't have been possible. A darkness so profound and so vast that it seemed to violate what we thought we knew about how big voids could grow. That darkness, that impossible emptiness, would come to be known as the Boötes Void, and its discovery would open questions that astronomers are still working to answer today. And this is where our exploration truly begins, with a mystery written in darkness across 330 million light-years of space. The story of the Boötes Void's discovery is, in many ways, the story of one astronomer's careful attention to patterns in data. Robert Kirshner, working at the University of Michigan in the late 1970s and early 1980s, was part of a team conducting a survey of galaxy redshifts. This might sound like esoteric work, and in a sense it was, but it was also fundamental to understanding how galaxies are distributed through space. A redshift survey works by measuring how much the light from distant galaxies has been stretched by the expansion of the universe. The more stretched the light, the more redshifted it appears, and the farther away the galaxy must be. By measuring redshifts for thousands of galaxies, astronomers can create a three-dimensional map of cosmic structure, revealing not just where galaxies appear in the sky, but how far away they are, and therefore how they're distributed through space. It's painstaking work, requiring clear nights, careful measurements, and months or years of telescope time. Kirshner and his colleagues were surveying galaxies in a region of the sky toward the constellation Boötes, a large constellation in the northern celestial hemisphere. Boötes isn't particularly famous. It doesn't have the mythological weight of Orion or the navigational importance of Ursa Major, but it occupies a substantial piece of sky, and it was as good a place as any to point their telescopes. As the survey progressed, as more galaxy redshifts were measured and plotted, something strange began to emerge in the data. There was a region, a substantial region, where galaxies simply weren't appearing. At first, this might not have seemed remarkable. Voids were already known to exist, regions of space where galaxy density was lower than average. But as more data came in, as the survey expanded and deepened, it became clear that this wasn't just a small void or a statistical fluctuation. This was something much larger, much emptier than any void previously discovered. The region that Kirshner's team was mapping appeared to contain almost no galaxies whatsoever, across a volume roughly 330 million light-years in diameter. To put that in perspective, our own Milky Way galaxy is about 100,000 light-years across. The distance to the nearest large galaxy, Andromeda, is about 2.5 million light-years. The local group, the cluster of galaxies that includes the Milky Way and Andromeda, spans about 10 million light-years. The Boötes Void was more than 30 times larger than the local group, a volume so vast that it should have contained thousands of galaxies, based on the average density of matter in the universe. Instead, it contained perhaps a few dozen. In cosmic terms, this was almost perfect emptiness, a hole in the universe so profound that when Kirshner's team published their findings in 1981, it immediately captured the attention and imagination of astronomers worldwide. Some called it the Great Void, others referred to it as the Boötes Supervoid. Popular accounts sometimes called it the Great Nothing, a name that captures something essential about its character. Kirshner himself was cautious in his interpretation, as good scientists tend to be. The void was real, the data was solid, but what did it mean? How could something so empty exist in a universe that had been expanding and evolving for billions of years? Was it truly as empty as it appeared, or were there galaxies lurking there that the survey had missed? And perhaps most intriguingly, what did the existence of such an enormous void tell us about the processes that had shaped the cosmic web? These questions would drive decades of follow-up research as astronomers pointed more powerful telescopes at the Boötes region, searching for galaxies that might have been missed, looking for clues about how such an enormous void could have formed, and contemplating what the existence of such structures meant for our understanding of cosmic evolution. And so we come to the question that would define much of the research that followed. What exactly is inside the Boötes Void, and what does its existence tell us about the universe we inhabit? Let's take a moment to truly contemplate the scale of what we're discussing, because numbers like 330 million light-years can become abstract if we're not careful. They can slide past our minds without leaving an impression of their true magnitude. So let's build up to this vast distance slowly, starting from something more familiar. Light moves at approximately 186,000 miles per second. In 1 year, light travels about 5.9 trillion miles, a distance we call a light year. When we look at the nearest star to our Sun, Proxima Centauri, we're seeing light that left that star 4.2 years ago. When we look at the centre of our own Milky Way galaxy, we're seeing light that began its journey 26,000 years ago, when humans were painting caves and living in small hunter-gatherer bands. When we look at the Andromeda Galaxy, we're seeing light that left 2.5 million years ago, when our ancestors were just beginning to make stone tools. And when we look at distant galaxy clusters, we're often seeing light that began travelling toward us billions of years ago before the Earth even existed. These distances are already difficult to grasp intuitively. They exist at a scale where human experience offers no useful comparison. The Boötes Void spans 330 million light-years. This means that if you could somehow travel at the speed of light, it would take you 330 million years to cross from one side of the void to the other. When light from the far side of the void reaches the near side, that light has been travelling for longer than the time that has passed since the dinosaurs went extinct, longer than the time that has passed since the Cambrian explosion, when complex life first appeared on Earth. It's a distance so vast that it encompasses a significant fraction of the observable universe's radius. Within this volume, if the universe's matter were distributed evenly, we would expect to find approximately 2,000 galaxies, perhaps more. Each of those galaxies would contain hundreds of billions of stars. Each of those stars would potentially host planets, moons, asteroid belts. The total amount of matter we would expect to find in such a volume is staggering, enough mass to create millions of solar systems, enough stars to light up that region of space with the soft glow of countless galaxies. Instead, the Boötes Void contains perhaps 60 galaxies. Perhaps. The exact number depends on where you draw the void's boundaries and how you define what counts as being inside versus on the edge of the void, But even if we use the most generous count, we're still talking about a galaxy density that's roughly 3% of what we'd expect, a deficiency so extreme that it represents one of the most underdense regions of space ever discovered. To visualize this, imagine a cube of space 100 million light-years on each side, roughly a third the diameter of the Boötes Void. In a typical region of the universe, such a cube would contain perhaps 200 galaxies, distributed in clusters and filaments according to the cosmic web's natural pattern. Now imagine removing 97% of those galaxies. What remains are a handful of small, faint galaxies scattered through an otherwise empty volume, like a few candles flickering in an enormous darkened cathedral. This emptiness isn't absolute, of course. The void isn't a perfect vacuum. It contains dark matter, that mysterious substance that doesn't emit light but does exert gravitational influence. It contains gas, primarily hydrogen and helium. spread so thinly that it barely registers on our instruments. It might contain dark energy, that even more mysterious force that seems to be accelerating the universe's expansion. Though dark energy is thought to be distributed evenly throughout space, rather than concentrated or absent in particular regions. What the void doesn't contain, in any meaningful quantity, is the bright organised matter that forms galaxies, stars and planets. And this raises a question that cosmologists have been working to answer for more than 4 decades. How did such an enormous region of space come to be so empty? What processes could have created a void this large, this empty? And how does its existence fit with our broader understanding of how the universe evolved from the nearly uniform plasma that filled space moments after the Big Bang to the complex structured cosmos we observe today? Let's turn our attention now to the theories that attempt to explain the Boötes Void's existence, and in doing so, we'll explore some of the fundamental principles that govern how structure forms in an expanding universe. The story of how voids form begins in the very early universe, in the first moments after the Big Bang, when space was filled with an incredibly hot, incredibly dense plasma of matter and energy. This plasma wasn't perfectly uniform. Quantum fluctuations in the very first moments after the Big Bang had created tiny variations in density, regions that were slightly more dense than average, and regions that were slightly less dense than average. These variations were minuscule, differences of only 1 part in 100,000, but they were enough. As the universe expanded and cooled, these tiny density variations began to grow through a process called gravitational instability. In regions that were slightly more dense than average, gravity was slightly stronger. This slightly stronger gravity pulled in more matter from surrounding regions, making those areas even denser. This created a feedback loop where the dense got denser and the sparse got sparser. With matter flowing from underdense regions toward overdense regions like water flowing downhill, over hundreds of millions of years, this process amplified the initial tiny fluctuations into the cosmic web we observe today. The overdense regions became galaxy clusters, the moderately dense regions became filaments, and the underdense regions became voids. This framework, called the theory of structure formation, is one of the most successful aspects of modern cosmology. It explains, with remarkable precision, how the universe went from nearly uniform to highly structured. But here's where the Boötes Void becomes interesting and slightly puzzling. According to our models of structure formation, voids should certainly exist, and large voids should be relatively rare but not impossible. When cosmologists run computer simulations of cosmic structure formation, feeding in the initial conditions we observe in the cosmic microwave background radiation and letting the laws of physics play out over billions of simulated years, they do get voids. Some of these simulated voids are quite large, but voids as large and as empty as the Boötes Void are uncommon even in these simulations. This doesn't mean the void violates our understanding of physics or cosmology. It means the Boötes Void is a rare structure, one that formed through a particular combination of initial conditions and evolutionary processes. Think of it like this. If you roll dice enough times, you'll occasionally get unusual results, not because the dice are loaded, but because unusual results are part of the natural distribution of outcomes. The Boötes Void might be cosmology's equivalent of rolling several sixes in a row, unusual but not impossible. The formation of such a large void would have required an initial region that was significantly underdense in the early universe, and then billions of years during which that underdensity was amplified by gravitational instability. Matter would have flowed out of this region toward denser regions nearby, leaving behind an increasingly empty volume. The few galaxies that did form within the void would be those that managed to collapse from local density peaks before all the surrounding matter was pulled away. There's also another factor to consider: expansion. The universe is expanding, and this expansion affects how voids evolve. In denser regions where galaxies are bound together by gravity, expansion doesn't have much effect on small scales. galaxies stay gravitationally bound to each other even as the space between galaxy clusters expands. But in voids, where there's little matter to resist expansion, the expansion of space itself works to make voids larger over time. This means that voids grow not just through matter flowing out of them, but through the expansion of space within them. Some researchers have suggested that the Boötes Void might have grown particularly large due to its environment. It's surrounded by relatively dense regions, galaxy clusters and superclusters that would have pulled matter away from the void's interior. This surrounding structure might have acted like a drainage system, pulling matter out of the void more efficiently than would happen in a more typical region of space. Over billions of years, this could have created the extreme emptiness we observe today. What's remarkable is that despite its size and emptiness, the Boötes Void doesn't fundamentally challenge our understanding of cosmology. It fits, albeit as an unusual example, within the framework that cosmologists have developed to explain large-scale structure. It's a reminder that the universe is vast enough to contain rare structures, that statistical outliers do occur when you have an entire cosmos to work with. And this brings us to a question that astronomers have pursued vigorously since the void's discovery. Are there actually any galaxies inside the void? And if so, what are they like? When the Boötes Void was first discovered, one of the immediate questions was whether it was truly as empty as it appeared. Perhaps, astronomers thought, there were galaxies within the void that the initial survey had missed. These might be smaller galaxies, or fainter galaxies, or galaxies that happened to be oriented in ways that made them harder to detect. So began a systematic effort to search the void more thoroughly, using more sensitive instruments and more refined techniques. What these follow-up surveys found was both confirming and intriguing. Yes, there are galaxies within the Boötes Void, but they are few, and they are unusual. The current best estimates suggest there are somewhere between 40 and 60 galaxies within the void's boundaries, compared to the 2,000 or more we would expect in a typical volume of that size. This confirms that the void is genuinely underdense, not just apparently empty due to observational limitations. But what's particularly interesting is the nature of these void galaxies. They tend to be smaller than average, with lower masses and lower luminosities than galaxies in denser regions. This makes sense when you consider how galaxies form and grow. In dense regions, galaxies frequently interact and merge, building up mass over time. They're surrounded by gas that they can accrete, fuel for forming new stars. They're part of a rich environment where interactions and mergers are common. Void galaxies, by contrast, exist in isolation. They formed from whatever local concentration of matter was available when they were born, and since then they've had little opportunity to grow through mergers or accretion. They're like islands in an empty ocean, cut off from the processes that make galaxies in denser regions larger and brighter. Many void galaxies are what astronomers call dwarf galaxies, containing perhaps a few billion stars compared to the hundreds of billions in large galaxies like our Milky Way. These void galaxies also tend to be younger in certain ways. They're actively forming stars, using up their available gas to create new suns. In denser environments, many galaxies have consumed most of their star-forming gas, or had it stripped away by interactions with other galaxies and the hot gas that fills galaxy clusters. Void galaxies, protected by their isolation, can continue forming stars over longer periods. They're quiet, steady, unhurried in their stellar production. From the perspective of a hypothetical civilization on a planet orbiting a star in a void galaxy, the night sky would be a remarkably lonely place. Where we on Earth can see thousands of stars with a naked eye and billions of galaxies with our telescopes, observers in a void galaxy would see their own galaxy's stars but little else. The nearest neighbouring galaxy might be tens of millions of light-years away, a faint smudge visible only with powerful instruments. The cosmic web structure, so evident to us, would be largely invisible, replaced by a vast darkness punctuated by only the most distant and faint galaxies. This raises philosophical questions that scientists sometimes ponder in quiet moments. If a civilization arose in a void galaxy, would they discover the same cosmology we have? Would they realise that their situation was unusual, that most galaxies exist in a richer, more connected cosmic environment? Or might they conclude that the universe is mostly empty space with rare islands of matter, a view that would be locally correct but globally misleading? Some astronomers have suggested that void galaxies might be ideal places to search for extraterrestrial intelligence, precisely because their isolation would make them scientifically interesting to any curious civilization. A civilization arising in such a galaxy might be driven to reach out, to search for others in the darkness, motivated by a profound cosmic loneliness. Of course, this is pure speculation, a blend of science and imagination, but it's the kind of speculation that the Boötes Void naturally inspires. What we know for certain is that the void is not completely empty, that it contains these small, isolated galaxies, each one a testament to the fact that even in the universe's quietest, darkest regions, structure and light can still emerge. And now, having established what the void is and what it contains, we can begin to explore the deeper mysteries that surround it, starting with one of the most persistent questions astronomers have faced. Could there be something in the void that we simply cannot see? When astronomers talk about the Boötes Void being empty, they're speaking specifically about visible matter, the kind of matter that forms stars and emits light that our telescopes can detect. But there's another kind of matter in the universe, something that makes up roughly 85% of all matter, but that we cannot see directly. This is dark matter, and understanding its role in the void is crucial to understanding what the void truly is. Dark matter doesn't interact with light. It doesn't emit photons, doesn't absorb them, doesn't reflect them. The only way we know dark matter exists at all is through its gravitational influence on visible matter, and on light itself. We see galaxies rotating faster than they should based on their visible mass alone. We see gravitational lensing effects where massive but invisible structures bend light from distant sources. We see the cosmic microwave background radiation showing patterns that only make sense if dark matter was present in the early universe, helping to seed the formation of structure. Everything we know about structure formation in the universe suggests that dark matter formed the scaffolding on which visible matter organized itself. Dark matter collapsed first, creating gravitational wells into which normal matter fell, eventually forming galaxies and stars. The cosmic web itself is primarily a dark matter web, with visible galaxies tracing out the underlying dark matter structure, like lights illuminating a framework. So what about the Boötes Void? Is it devoid of dark matter as well as visible matter, or does it contain dark matter in quantities similar to the rest of the universe? This question has important implications. If the void contains normal amounts of dark matter, but little visible matter, that tells us something interesting about how galaxy formation works. If the void is also deficient in dark matter, that tells us something different about the initial conditions that led to the void's formation. Current evidence suggests that the Boötes Void is indeed deficient in dark matter, though not as dramatically as it is deficient in visible matter. Computer simulations of large-scale structure formation that include dark matter show that voids form in regions where dark matter was initially less dense, and that these voids remain somewhat underdense in dark matter even as they grow larger. The gravitational influence of surrounding overdense regions pulls dark matter out of voids, just as it pulls visible matter, though the effect is somewhat less extreme. What this means is that the void isn't completely empty, even of dark matter. There's a diffuse distribution of dark matter throughout the void's volume, creating a weak gravitational field but not enough of a gravitational pull to have prevented the void from expanding to its current enormous size. This dark matter provides some gravitational attraction, enough perhaps to influence the motions of the few galaxies that do exist within the void, but not enough to have captured and retained the quantities of normal matter that would have been needed to form a normal density of galaxies. Measuring the dark matter content of voids is challenging, because dark matter only reveals itself through gravitational effects, and in a region where there's little visible matter to show those effects, detection becomes difficult. Astronomers use techniques like weak gravitational lensing, looking for subtle distortions in the light from distant galaxies that passes through or near the void. But these measurements require extremely precise observations and careful statistical analysis. What we're left with is a picture of the Boötes Void as a region that is underdense in all types of matter, both visible and dark, but particularly underdense in visible matter. The dark matter that is present provides a faint gravitational framework, but one too weak to have prevented the void from growing to its current size or to have captured significant amounts of gas for galaxy formation. This understanding connects back to our earlier discussion of how voids form, the initial underdensity in both dark and visible matter in the region that would become the Boötes Void, combined with the surrounding overdense regions pulling matter away, created a feedback loop that resulted in the extreme emptiness we observe today. Dark matter and Before we continue, I want to pause for just a moment, because what you have learned in the last 30 minutes is something genuinely rare. Most people move through their entire lives without ever stopping to understand the world at this level, but you did. Tonight you chose curiosity over noise and depth over distraction. That is exactly who this channel was made for. If you want to keep being that person, a like and subscribe takes 2 seconds and make sure this channel never stops finding you. Now, let's go deeper. Dark matter and visible matter both participated in this process. Though dark matter's purely gravitational nature means it responds somewhat differently to the expansion and evolution of cosmic structure. And this brings us to consider another invisible component of the universe, one that's even more mysterious than dark matter, and that might play a role in the void's existence and evolution. If dark matter is mysterious, dark energy is doubly so. We know even less about what dark energy is or how it works, yet it appears to make up roughly 68% of all the energy in the universe. Dark energy is the name we give to whatever is causing the expansion of the universe to accelerate, a discovery made in the late 1990s that earned its discoverers the Nobel Prize and fundamentally changed our understanding of cosmic evolution. Before the discovery of cosmic acceleration, cosmologists expected that the expansion of the universe would gradually slow down over time due to the gravitational attraction of all the matter it contains. The universe would expand forever, perhaps, or it might eventually contract in a big crunch, but either way, gravity should be working to slow the expansion. Instead, observations of distant supernovae reveal that the expansion is speeding up, that galaxies are accelerating away from each other, as if driven by some repulsive force that permeates all of space. This force, this dark energy, is thought to be a property of space itself, a kind of energy density inherent to the vacuum. The more space there is, the more dark energy there is, and the stronger its repulsive effect becomes. Einstein's equations of general relativity can accommodate such an energy through what's called the cosmological constant, a term Einstein himself added and then removed from his equations, but which modern observations suggest is actually necessary to explain what we observe. Now, what does dark energy have to do with the Boötes Void? This is a question that cosmologists have explored with great interest, because voids might be places where dark energy's effects are particularly evident. In dense regions filled with galaxies, matter's gravitational attraction is strong enough to overcome dark energy's repulsive effect on small scales. Galaxies remain bound together, clusters remain intact, the cosmic web's filaments persist despite the universe's overall expansion. But in voids, where matter is sparse and gravity is weak, dark energy's effect might dominate. This could mean that voids are expanding faster than the universe as a whole, that the space within voids is being stretched by dark energy's influence more rapidly than space in denser regions. Over billions of years, this differential expansion could contribute to making voids larger and emptier, exacerbating the initial underdensity that created the void in the first place. Some researchers have proposed that careful measurements of how voids expand over time could provide insights into dark energy's properties. If we could measure the expansion rate within the Boötes Void and compare it to expansion rates in denser regions, we might learn something about how dark energy interacts with matter and space. These measurements are extraordinarily difficult to make, requiring precise observations over many years to detect the subtle changes in galaxy positions and velocities, but they represent one of the ways that studying voids might advance our understanding of fundamental physics. There's also a more speculative idea that occasionally surfaces in cosmological discussions. Could regions like the Boötes Void be places where dark energy's density is different from the cosmic average? Most models assume that dark energy is uniformly distributed throughout space, that its density is the same everywhere. But what if that assumption is wrong? What if dark energy can vary in density from place to place? And what if voids are regions where dark energy's density is higher than average? This idea is intriguing but faces significant theoretical challenges. Most models of dark energy predict uniform distribution, and observations of the cosmic microwave background and large-scale structure generally support this uniformity. Still, the possibility remains open enough that some researchers continue to explore whether voids could be laboratories for testing theories of dark energy and its properties. What we can say with more confidence is that dark energy plays some role in void evolution, even if we're not yet certain about the details. As the universe ages and dark energy's influence becomes increasingly dominant over matter's gravitational attraction, voids will likely continue to grow, becoming larger and emptier as the space within them expands and the few galaxies they contain accelerate away from each other. In the far future, billions of years from now, voids might dominate the universe's volume, with matter concentrated into ever denser clusters separated by ever larger expanses of nearly empty space. The Boötes Void, then, might give us a preview of the universe's distant future, a glimpse of what most of space might eventually become as dark energy drives an eternal acceleration of cosmic expansion. Let's consider now what happens to light itself as it travels through such empty regions of space. Imagine a photon, a particle of light, emitted from a galaxy on the far side of the Boötes Void and travelling toward Earth. This photon begins its journey surrounded by the normal matter and energy of its home galaxy, but as it leaves that galaxy and enters the void proper, it enters a very different environment. For the next 330 million years, travelling at the speed of light, this photon crosses through a region where encounters with matter become extraordinarily rare. Light travelling through normal regions of the universe frequently interacts with matter. It might be absorbed by a dust grain and re-emitted at a different wavelength. It might be scattered by an electron in a cloud of gas. It might pass close to a massive object and have its path bent by gravitational lensing. These interactions leave their mark on the light, changing its properties in ways that astronomers can measure and interpret. But in the Boötes Void, these interactions become vanishingly unlikely. The density of gas is so low, the number of dust grains so sparse, that a photon can travel for millions of light years without encountering anything substantial enough to scatter or absorb it. This makes void crossings remarkably clean. Photons that enter a void on one side will almost certainly exit on the other side, with their properties largely unchanged by any interaction with matter. This has interesting implications for astronomy. When we observe distant objects through or beyond the Boötes Void, we're seeing them through a remarkably transparent medium. There's no intervening forest of galaxies to confuse the signal, no dense clouds of gas to absorb certain wavelengths. The void acts almost like a perfect window, allowing us to see distant structures with unusual clarity. Some astronomers have used this property to study objects that lie beyond the void, taking advantage of the void's transparency to get clear views of distant galaxy clusters and superclusters. However, the photon does experience one important effect during its void crossing: cosmological redshift. As the photon travels through expanding space, its wavelength gets stretched by the expansion of the universe. This happens everywhere in the universe, not just in voids. But the effect accumulates over distance. A photon that crosses the entire Boötes Void will experience significant redshift, its wavelength stretched by the expansion of 330 million light-years worth of space. There's also a subtle effect called the integrated Sachs-Wolf effect that's worth mentioning. When a photon enters a void, it's falling into a gravitational potential well, however shallow, and it gains a tiny amount of energy. When it exits the void, it climbs back out of that potential well and loses that energy. Normally these effects would cancel out, but because the universe is expanding and because dark energy is causing that expansion to accelerate, the potential well is shallower when the photon exits than when it entered. The photon gained more energy falling in than it loses climbing out, resulting in a net blue shift. This effect is incredibly tiny and difficult to measure, but it's been detected in statistical studies of the cosmic microwave background radiation passing through large voids. It provides one more piece of evidence for dark energy's existence and properties, and it shows that even in crossing empty space, light carries information about the universe's structure and evolution, for our photon crossing the Boötes Void. The void's few galaxies, feeling a tiny gravitational tug as it passes, but mostly its journey is one of uninterrupted travel through expanding space, a straight line across darkness. When that photon finally reaches Earth and enters one of our telescopes, it carries with it a record of its journey. Its wavelength tells us about the universe's expansion. Its direction tells us about the large-scale structure it passed through. Its intensity tells us about the object that emitted it. And the very fact that it arrived largely unaltered tells us about the emptiness it crossed, about the void that lies between us and its source. This property of voids, their transparency to light, makes them valuable for certain types of astronomical observations, but it also raises questions about what else might exist in the void that doesn't interact with light in ways we can easily detect. Could there be structures or phenomena in the void that are invisible to our telescopes, things that don't emit or absorb electromagnetic radiation, but that exist nonetheless? Let's explore what might be hiding in the darkness, invisible to our eyes and instruments. Our understanding of the Boötes Void is built on observations, and observations have limits. We can only detect what emits or affects light in ways our instruments can measure. This means there could be things in the void that exist, but that we simply cannot see with current technology. Let's explore some of the possibilities, starting with the most mundane and moving toward the more speculative. First, there's cold gas. The void almost certainly contains diffuse clouds of hydrogen and helium, the primordial elements left over from the Big Bang. Most of this gas is probably neutral, meaning it's not ionized and therefore doesn't emit the kind of radiation that would make it easily detectable. At the densities expected in voids, this gas would be extraordinarily difficult to observe directly. It might reveal itself through absorption lines in the spectra of background objects, or through the faint 21 centimeter radio emission from neutral hydrogen. But detecting these signals requires sensitive instruments and careful observation. This cold gas is important because it represents the raw material from which future galaxies might form if the void's expansion ever slows enough to allow gravitational collapse to occur. It's also a reservoir of matter that contributes to the void's overall mass budget, even though we can't see it easily. Estimating how much cold gas exists in the void involves theoretical modelling based on what we know about the early universe and the processes that distributed matter throughout space. Then there are primordial black holes, hypothetical objects that might have formed in the very early universe, fractions of a second after the Big Bang, from density fluctuations that collapse directly into black holes rather than forming matter structures. If primordial black holes exist, they could be scattered throughout the universe, including through voids. These black holes would be dark, emitting no light unless they happen to be actively accreting matter, which in the void's sparse environment would be unlikely. detecting primordial black holes is challenging. Astronomers look for gravitational lensing effects, microlensing events where a black hole passes in front of a background star and briefly magnifies its light. They also look for gravitational wave signals from black hole mergers, but a primordial black hole drifting alone through the Boötes Void would be essentially invisible unless it happened to pass directly between us and a background light source. The void could contain millions of such objects, and we would have no direct way of knowing they were there. Moving into more speculative territory, there are various exotic structures that theoretical physics allows, but that we have no confirmed observations of. These include cosmic strings, one-dimensional defects in space-time that might have formed during phase transitions in the very early universe. Cosmic strings, if they exist, would be extraordinarily dense and would have significant gravitational effects. But they could potentially cross through voids without creating visible structures, detectable only through subtle lensing effects or gravitational wave emissions. There are also hypothetical dark matter structures that might not have any associated visible matter. Most dark matter halos contain galaxies, but perhaps there exist dark matter concentrations that fail to capture enough normal matter to form stars. These dark halos would be completely invisible except through gravitational lensing, and in a void where background light sources are sparse, detecting such structures would be extraordinarily challenging. Some researchers have even speculated about whether voids could contain unusual forms of matter or energy that don't fit into our current physics framework. These ideas are highly speculative and not supported by current evidence, but they remind us that our understanding of the universe is still incomplete. Dark matter and dark energy themselves were once considered exotic possibilities, and they turned out to be the dominant forms of matter and energy in the cosmos. It's not impossible that there are other phenomena awaiting discovery. What's important to remember is that absence of evidence is not evidence of absence. When we say the Boötes Void is empty, we mean it's empty of the things we can detect with current technology. There could be a rich hidden universe of dark structures, cold gas, exotic particles, and phenomena we haven't yet imagined. The void might be far more populated than it appears, just populated with things that don't shine. This uncertainty, this acknowledgement of the limits of our knowledge, is a fundamental part of scientific honesty. Astronomers can only report what they observe and what they can infer from theory. The Boötes Void appears to be remarkably empty based on all available evidence, but quote 2 is not the same as quote 3. There's always room for surprise. Always the possibility that future observations with more sensitive instruments will reveal structures we cannot currently see. And this brings us to consider how astronomers are working to map the void more thoroughly, using new technologies and new techniques to peer ever deeper into that cosmic darkness. Since Robert Kirshner's initial discovery in 1981, astronomers have returned to the Boötes Void again and again, using increasingly sophisticated instruments and techniques to map its structure and search for objects that earlier surveys might have missed. This ongoing effort to characterize the void represents some of the most careful and patient work in observational astronomy, and it has revealed details that the initial discovery could not have detected. Modern redshift surveys use spectrographs that can measure hundreds or thousands of galaxy redshifts simultaneously, dramatically increasing the efficiency of mapping large regions of space. Projects like the Sloan Digital Sky Survey have mapped millions of galaxies across substantial fractions of the sky, creating three-dimensional maps of cosmic structure with unprecedented detail. When these surveys examine the region of the Boötes Void, they confirm what Kirshner found. The void is real, it's large, and it's remarkably empty. But they also reveal structure within the void that wasn't apparent in earlier work. The void isn't perfectly spherical or perfectly empty. It has a complex shape with tendrils and extensions, regions that are more empty and regions that are less empty. There are small galaxy groups along the void's edges, structures that might be best thought of as part of the void's boundary rather than truly interior to it. And there are those few dozen galaxies scattered through the interior, islands in an empty ocean. Mapping efforts have also used different wavelengths of light to search for different types of objects. Radio surveys look for neutral hydrogen gas and radio galaxies. Infrared surveys can detect cooler objects that might be invisible in visible light. X-ray surveys search for hot gas and active galactic nuclei. Each wavelength provides a different view of the void, and together they build up a more complete picture of what exists there. One particularly interesting technique involves using the cosmic microwave background radiation, the afterglow of the Big Bang that fills all of space. When CMB photons pass through large voids, they experience the integrated Sachs-Wolf effect we discussed earlier, creating a subtle temperature signal that can be detected through careful statistical analysis. Researchers have used this technique to study the Boötes Void and other large voids, measuring their gravitational potential and inferring their matter content. Gravitational lensing surveys offer another approach. Even though the void contains little visible matter, it does contain some mass, and that mass creates gravitational fields that can bend light from more distant sources. By carefully measuring the shapes and positions of distant galaxies seen through or near the void, astronomers can map the distribution of both visible and dark matter in the void's vicinity. These weak lensing surveys require enormous amounts of data and sophisticated analysis, but they provide unique insights into the void's total mass content. What all these surveys consistently show is that the void is genuinely underdense, that it's not simply an artifact of earlier observational limitations. The modern best estimate is that the void's interior has a galaxy density about 3 to 10% of the cosmic average, depending on exactly where you draw the void's boundaries. This extreme underdensity makes the Boötes Void one of the largest and most prominent voids in the observable universe, though not necessarily the largest ever discovered. Astronomers have found other voids that rival or exceed the Boötes Void in size, including several supervoids discovered in more recent surveys. Each of these represents a rare but natural part of cosmic structure, examples of how matter organizes itself on the larger scales. The existence of multiple large voids helps confirm that structures like the Boötes Void are unusual but not unique, that they arise naturally from the processes that govern cosmic evolution. Looking ahead, new instruments and surveys promise to map the void in even greater detail. Projects like the Large Synoptic Survey Telescope, now called the Vera C. Rubin Observatory, will observe billions of galaxies and create the most detailed three-dimensional map of cosmic structure ever made. When this survey examines the Boötes region, it will likely find more of the faint dwarf galaxies that populate the void, refining our census of what exists there. Future radio surveys might detect more of the cold gas in the void, measuring its distribution and properties. Gravitational wave observatories might detect black hole mergers or other events occurring in or near the void. Each new observational capability adds to our understanding, filling in details and sometimes raising new questions about what we're seeing. And this brings us to a question that naturally follows from all this careful observation. How does the Boötes Void compare to other voids in the universe? Is it truly unusual, or is it simply the first of its kind to be discovered? The Boötes Void is not alone. Since its discovery, astronomers have identified hundreds of voids throughout the observable universe, ranging from relatively small voids tens of millions of light-years across to enormous supervoids that rival or exceed the Boötes Void in size. This population of voids is an essential part of the cosmic web structure, occupying roughly 80% of the universe's volume, even though they contain only a tiny fraction of its galaxies. One of the most studied voids is the local void, a region roughly 150 million light-years across that lies relatively close to our own Milky Way galaxy. The local void is smaller than the Boötes Void, but is interesting precisely because of its proximity. We sit near its edge, and studying it gives astronomers a detailed view of void structure that's harder to achieve with more distant voids. The local void contains perhaps 200 galaxies, making it less empty than the Boötes Void in terms of galaxy density. but still dramatically underdense compared to typical cosmic regions. Then there are the supervoids, structures that push the limits of how large voids can grow. The Eridanus supervoid is a region roughly 1 billion light-years across that was identified through its effect on the cosmic microwave background radiation. This void is so large and so underdense that it creates a measurable cold spot in the CMB, a region where the temperature is slightly cooler than the cosmic average due to the integrated Sachs-Wolf effect. The existence of such an enormous void has sparked discussions about whether structures this large are consistent with standard cosmological models. The CMB cold spot itself has been a subject of considerable debate. Some researchers have suggested that the temperature anomaly might indicate something even more exotic than a large void, perhaps a sign of cosmic topology or parallel universes. However, the current consensus is that the cold spot can be explained by the combination of the Eridanus supervoid and several smaller voids along the line of sight, creating a cumulative effect on the CMB photons passing through these underdense regions. Another remarkable structure is the giant void in the constellation Canes Venatici, which spans approximately 1 billion light-years and contains only a few known galaxies. This void was discovered relatively recently using data from the Sloan Digital Sky Survey, demonstrating that even in the 21st century, astronomers are still finding enormous structures that earlier surveys missed. The giant void challenges our understanding of how common such extreme structures should be in a universe governed by the standard cosmological model. What's interesting about studying multiple voids is that it allows astronomers to understand void statistics, to determine how common voids of different sizes are and whether the distribution of void sizes matches theoretical predictions. In general, smaller voids are much more common than larger ones, following a pattern that's consistent with structure formation theory. The largest voids, like the Boötes Void and the supervoids, are rare but not so rare that their existence contradicts our models. Each void has its own character, its own shape and environment. Some voids are relatively spherical, while others are elongated or irregular. Some voids are well defined with clear boundaries, while others blend gradually into surrounding regions of average density. Some voids are isolated, while others are connected to other voids through low-density regions, creating a complex network of empty space. These variations tell us about the initial conditions in different regions of the early universe, and about how those regions have evolved over billions of years. A spherical void might have formed from a single, isolated, underdense region in the early universe. An elongated void might have formed from a chain of smaller, underdense regions that merged over time. The shape and structure of voids contain information about cosmic history, if we can learn to read it correctly. Astronomers have also discovered that voids are not static. They're evolving, growing larger as matter continues to flow out of them toward denser regions, and as the expansion of space stretches them. By comparing the properties of nearby voids to more distant voids, which we see as they were in the past due to light's finite travel time, astronomers can study how voids change over cosmic time. This evolution is generally consistent with theoretical predictions, providing another confirmation that our understanding of structure formation is fundamentally correct. One particularly interesting question is whether there's a maximum size for voids. Could voids grow arbitrarily large, given enough time and the right initial conditions, or is there some physical limit to how large they can become? Current observation suggests that while voids can become very large, the largest ones we observe are roughly consistent with what we'd expect from extrapolating structure formation theory to its extremes. Voids much larger than the biggest supervoids we've found would be so rare that we might not expect to see them in the observable universe. The existence of this void population, from small to enormous, helps put the Boötes Void in context. It's a remarkable structure, certainly one of the largest and most empty voids known. But it's part of a continuum of void structures that together shape the universe's large-scale architecture. Understanding the Boötes Void means understanding voids in general, and understanding voids means understanding how the cosmic web formed and evolved. And this brings us to consider what role voids play in the broader cosmic structure, how they fit into the universe's evolution, and what they tell us about the fundamental processes that govern the cosmos. To truly understand what voids mean for cosmology, we need to think about the universe's structure in terms of both positive and negative space, both the places where matter has gathered and the places from which it has departed. Voids are not simply empty regions that happen to exist between structures. They're an integral part of the structure itself, the necessary complement to galaxy clusters and filaments. Think of it this way: matter is conserved in the universe. For regions to become overdense, other regions must become underdense. The process of gravitational instability that creates galaxy clusters and superclusters necessarily creates voids as its counterpart. Matter flows from underdense regions toward overdense regions. And this flow is what sculpts the cosmic web into its characteristic pattern of clusters, filaments, and voids. You cannot have one without the others. This means that studying voids provides information about cosmic structure that complements what we learn from studying galaxy clusters. Clusters tell us about how matter concentrates and evolves in dense environments. Voids tell us about how matter evacuates from underdense regions, and about how structure formation proceeds in the universe's quiet, empty places. Together, clusters and voids give us a complete picture of large-scale structure. Voids also provide a clean environment for testing certain aspects of cosmological theory. In dense regions, many complex processes are occurring simultaneously. Galaxies are merging, gas is being heated and stripped, stars are forming and exploding, black holes are growing and emitting radiation. All of these processes can affect observations in ways that are difficult to disentangle from the underlying cosmological signals we're trying to measure. In voids, many of these complications are absent or minimized. The few galaxies that exist there are relatively isolated and undisturbed. The gas is cold and sparse. The environment is quiet. This makes voids ideal laboratories for certain types of measurements, particularly those related to the expansion of the universe and the properties of dark energy. For example, astronomers use a technique called Alcock-Paczynski test, which involves measuring the shape of voids in three-dimensional space. The apparent shape of a void depends on the universe's expansion rate in the direction along our line of sight versus perpendicular to it. By measuring void shapes carefully, astronomers can constrain the expansion history of the universe, providing an independent check on measurements made using other techniques like supernova observations or baryon acoustic oscillations. Voids also play a role in understanding how galaxies form and evolve. The galaxies within voids provide natural experiments in galaxy formation in isolation. Environment matters significantly. Galaxies in dense regions tend to be older, more massive and redder, meaning they've stopped forming stars, while void galaxies tend to be younger, less massive and bluer, meaning they're actively forming stars. This environmental dependence tells us that galaxy evolution isn't determined solely by a galaxy's initial mass or its internal properties. The surrounding environment, the availability of gas to accrete, the frequency of interactions with other galaxies, all of these factors influence how a galaxy develops over cosmic time. Voids, by providing an environment with minimal interactions, show us what galaxies look like when they evolve in isolation. There's also a philosophical dimension to thinking about voids as part of cosmic structure. We often focus on the bright, active parts of the universe, the galaxies, the star-forming regions, the energetic phenomena like quasars and supernovae. But the universe is mostly empty space. The voids, those vast dark regions, make up the bulk of cosmic volume. In a sense, the universe is primarily defined by what isn't there, by the absences and emptiness, with matter and light being the exception rather than the rule. This perspective shifts how we think about our place in the cosmos. We live in one of the universe's bright, dense regions, part of a galaxy cluster that's part of a larger supercluster. From our perspective, the universe seems full of galaxies and structure. But we're living in an exceptional location. Most of space is void, empty and dark and silent. If you could place yourself at a random location in the universe, you would almost certainly find yourself in a void, with the nearest galaxy millions of light years away, and the nearest galaxy cluster hundreds of millions of light years distant. The Boötes Void, then, represents something closer to the universe's typical state than our own crowded cosmic neighbourhood does. It shows us what most of reality is actually like: vast, empty, and profoundly dark, punctuated only occasionally by small islands of light and matter. Understanding voids means understanding that the universe's default state is emptiness, and that the structures we see, the galaxies and clusters and superclusters, are elaborate but ultimately rare exceptions to that emptiness. This realization can be humbling, but it can also be strangely comforting. The universe doesn't need to be full to be remarkable. The emptiness itself is part of the story, part of the beauty, part of what makes the bright places meaningful. Let's turn now to consider how voids might help us understand one of cosmology's greatest mysteries, the nature of dark energy and the ultimate fate of the universe. The discovery that the universe's expansion is accelerating, driven by dark energy, fundamentally changed our picture of cosmic evolution and the universe's ultimate fate. Before this discovery, cosmologists debated whether the universe would expand forever, gradually slowing down or eventually contract in a big crunch. Now we know that neither of these simple scenarios is correct. The expansion is accelerating, and if this acceleration continues, the universe faces a very different future. In this dark, energy-dominated scenario, the universe will continue expanding faster and faster. Galaxy clusters that are currently bound together by gravity will remain bound, but clusters will accelerate away from other clusters. Eventually, the space between galaxy clusters will expand so rapidly that light from one cluster will never be able to reach another. The observable universe from any given location will shrink to include only the local galaxy cluster, with everything else disappearing beyond a cosmic horizon. Voids will play a significant role in this evolution. As dark energy's influence becomes increasingly dominant, voids will grow faster, expanding more rapidly than the universe as a whole. Matter that currently exists in void galaxies or in gas clouds within voids will be pulled toward the nearest dense regions, leaving the voids even emptier. The universe will become increasingly dominated by void volume. With matter concentrated into island clusters separated by ever larger expanses of nearly empty space, the Boötes Void might give us a preview of this future. Its extreme emptiness, the isolation of its few galaxies, the vast distances between any structures within it, all of these characteristics might represent what most of the universe will eventually become. In billions of years, what we now think of as normal regions of space might come to resemble the current state of the Boötes Void, with galaxies becoming rare exceptions in an ocean of expanding emptiness. But voids might also help us understand whether this dark energy-dominated future is inevitable. One of the crucial questions in modern cosmology is whether dark energy is truly constant over time or whether its strength might change. If dark energy is Einstein's cosmological constant, then its density remains fixed even as the universe expands, and the accelerating expansion will continue forever. But if dark energy is something more dynamic, a field that can evolve over time, then its strength might change, potentially even reversing the acceleration. Studying how voids have evolved over cosmic history might provide clues about dark energy's nature. By comparing nearby voids to distant voids, which we see as they were billions of years ago, astronomers can measure whether voids have been growing at a constant rate, or whether their growth has been accelerating or decelerating. These measurements can constrain models of dark energy, helping determine whether it's constant or evolving. Current observations suggest that dark energy has been relatively constant over at least the past several billion years, consistent with the cosmological constant interpretation. But the measurements are still improving, and future observations of void evolution might reveal subtle changes that would point toward a more complex theory of dark energy. This would have profound implications for the universe's ultimate fate. There's also the question of what happens inside voids on timescales much longer than the current age of the universe. If the accelerating expansion continues indefinitely, will the few galaxies in voids eventually be torn apart by the expansion of space? Current models suggest that gravitationally bound structures, including galaxies, will remain intact even as the space between them expands. But on truly cosmic timescales, tens or hundreds of billions of years in the future, even these structures might be affected by the universe's acceleration. Some cosmologists have speculated about a scenario called the Big Rip, where dark energy strength increases over time until it becomes strong enough to overcome all forces holding structures together. In this scenario, galaxy clusters would be torn apart first, then individual galaxies, then solar systems, then planets, then eventually atoms themselves. Everything would be ripped apart by the accelerating expansion of space. Voids would expand catastrophically, growing without limit until they encompassed everything. This Big Rip scenario is considered unlikely based on current observations, but it remains a theoretical possibility that can't be completely ruled out. Studying voids and their evolution helps constrain whether such extreme scenarios are possible. So far, the evidence suggests that dark energy is relatively gentle, accelerating the expansion, but not in a way that threatens gravitationally bound structures. But continued observation is necessary to be certain. There's something profound about the idea that the emptiest regions of the current universe might represent what most of the universe will eventually become. It suggests that emptiness is not just a temporary state, but perhaps the universe's ultimate destiny, with the current age of stars and galaxies being a brief, bright interval between the dense early universe and the sparse, dark future universe. In this view, voids like the Boötes Void are not anomalies but previews, glimpses of the long night that awaits the cosmos. Yet even in this dark future, there will be light. The galaxies within galaxy clusters will continue to exist, potentially for trillions of years. Stars will continue to shine, though eventually they will exhaust their fuel and fade. Life, if it exists elsewhere in the universe, will have unimaginable stretches of time to evolve and develop. The future may be dark and empty on the larger scales, but it will also be long, perhaps infinitely so, offering possibilities we can barely imagine. And this brings us to consider a question that naturally arises when contemplating such vast expanses of emptiness. Could life exist in a void galaxy? And what would it be like to look out at the universe from such a profoundly isolated location? Imagine, if you will, a planet orbiting a star in one of the small galaxies within the Boötes Void. This planet might be very much like Earth, with continents and oceans, an atmosphere, perhaps even life that has evolved over billions of years. But the night sky from this planet would be unlike anything we experience from Earth. And the astronomy developed by any intelligent beings, there would lead them to very different conclusions about the nature of the universe. From Earth, when we look up on a clear, dark night far from city lights, we can see thousands of stars with the naked eye. These are all stars within our own Milky Way galaxy. We can also see the Andromeda galaxy as a faint smudge, and with good conditions, a few other nearby galaxies. Our telescopes reveal billions more galaxies scattered across the cosmos, showing us that we live in a universe rich with structure and light. But from a planet in a void galaxy, the view would be starkly different. The night sky would show the stars of that galaxy, perhaps a few billion suns scattered across the darkness. These stars would be familiar and comforting, just as our stars are to us. But beyond those stars, there would be almost nothing. The nearest other galaxy might be 50 or 100 million light-years away, far too distant to see with the naked eye and barely visible even with powerful telescopes. An astronomer on such a world developing a telescope and beginning to map the universe would initially conclude that their galaxy was alone, that it constituted the entire universe. They might discover the expansion of their galaxy, the rotation of stars around its centre, the evolution of stars from birth to death. But they would see no other galaxies, no cosmic web, no evidence of a universe beyond their own island of light. Eventually, with sufficiently powerful telescopes and patient observation, they might detect one or two of the nearest void galaxies, faint smudges at the limit of detectability. This would revolutionize their understanding, revealing that their galaxy was not alone, that other island universes existed in the darkness. But even then, their view of cosmic structure would be incomplete. They might not realize that they lived in an unusually empty region, that most of the universe was more richly populated with galaxies than their neighborhood was. This raises a fascinating question in the history and philosophy of science. How much does our location in the universe affect our understanding of it? We develop theories based on what we can observe. But what if our location is unusual in ways that bias our observations? Could there be aspects of the universe that we miss because we happen to live in a particular type of environment? For the hypothetical astronomers in a void galaxy, their isolation might lead them to overestimate how rare galaxies are in the universe as a whole. They might develop a cosmology in which galaxies are few and far between, separated by vast emptinesses. They would be locally correct but globally wrong, not realizing that they lived in an exceptional location. Similarly, we on Earth might have our own biases based on our location. We live in a relatively dense region of the universe, part of a galaxy group that's part of a larger supercluster. Does this affect our understanding of cosmic structure? Do we overestimate how common galaxies are, how connected the cosmic web is? Probably not to any significant degree, since we can observe the full range of environments from dense to sparse, but it's worth considering. There's also the psychological and philosophical impact to consider. For the beings in a void galaxy, if they exist, the universe might seem like a lonelier place than it does to us. The knowledge that the nearest other galaxy was tens of millions of light years away, forever unreachable even at the speed of light, might create a profound sense of cosmic isolation. It might affect their art, their philosophy, their religions, their entire world view. On the other hand, such isolation might create a powerful drive to understand the universe precisely because it seems so empty. Why are we alone? Are we truly alone? What happened to create such emptiness? These questions might motivate a deep commitment to astronomy and physics, a determination to understand their place in the cosmos. The rarity of other galaxies might make each discovery of a distant galaxy more precious, more meaningful than it is for us in our galaxy-rich environment. From our perspective, there's something poignant about the idea of a civilization arising in a void galaxy, looking out at an almost empty universe, possibly not knowing that elsewhere, in regions like our own, galaxies cluster together in rich groups and superclusters. It makes us appreciate our own cosmic neighborhood, the fact that we have thousands of galaxies within relatively easy observational reach, that we can study the full diversity of cosmic structure without needing to look billions of light years away. It also reminds us that the universe is vast enough to contain many different types of environments, many different perspectives on cosmic reality. What seems normal from one location might seem exceptional from another. The universe has no single correct view, no privileged observational position. Each location offers its own perspective, its own window into the whole, and perhaps this is part of what makes the universe so rich and interesting, the fact that it contains both dense regions and empty voids, both crowded galactic neighborhoods and isolated island galaxies, both locations where the cosmic web is obvious and locations where it's nearly invisible. The diversity of environments is part of the universe's character, part of what makes it more than just a uniform distribution of matter and energy. Let's consider now how our understanding of the Boötes Void has evolved over the decades since its discovery, and what new questions have emerged as we've learned more about this remarkable region of space. When Robert Kirshner first announced the discovery of the Boötes Void in 1981, it immediately sparked debate and discussion in the astronomical community. Some researchers questioned whether the void was real, or whether it might be an artifact of incomplete observations. Others accepted the void's existence, but debated what it meant for cosmological theory. Over the decades since, our understanding of the void has evolved considerably, shaped by new observations, improved theories, and the broader context of advances in cosmology. In the early years after its discovery, one of the main questions was whether the void was truly as empty as it appeared. Several observational campaigns were launched to search more thoroughly for galaxies within the void, using increasingly sensitive instruments to look for faint objects that earlier surveys might have missed. Was real and not simply due to observational limitations. Through the 1990s, as redshift surveys expanded and became more comprehensive, astronomers discovered other large voids, helping to put the Boötes Void in context. It became clear that while the Boötes Void was exceptionally large and empty, it wasn't unique. Large voids were a natural, if rare, component of cosmic structure. This helped alleviate concerns that the void's existence somehow contradicted cosmological theory. The development of large-scale structure simulations in the 1990s and 2000s provided another crucial piece of understanding. When cosmologists ran computer simulations of how the universe's structure evolved from the initial conditions we observe in the cosmic microwave background, these simulations naturally produced voids of various sizes. The largest voids in these simulations were comparable to the Boötes Void, suggesting that its existence was consistent with standard cosmological models. However, some researchers noted that voids as large as the Boötes Void were relatively rare even in simulations, occurring only occasionally in volumes the size of the observable universe. This raised subtle questions about whether the cosmological model needed minor adjustments to explain the population of large voids, but these concerns were never severe enough to suggest fundamental problems with the theory. The discovery of cosmic acceleration and dark energy in the late 1990s added a new dimension to thinking about voids. Researchers began to explore how dark energy might affect void evolution, and whether voids could be used as tools for studying dark energy's properties. This sparked a renewed interest in precisely measuring void sizes, shapes, and evolution over cosmic time. In the 2000s and 2010s, improved observational techniques, including gravitational lensing surveys and cosmic microwave background studies, provided new ways to probe the void's properties. These observations confirmed that the void was deficient in dark matter as well as visible matter, and they provided increasingly precise measurements of just how underdense the void truly was. The picture that emerged was consistent with the void having formed from a naturally occurring underdense region in the early universe that had been amplified by billions of years of structure formation. Throughout this evolution of understanding, certain questions have persisted. How common are voids of this size? Are there even larger voids waiting to be discovered? What do the largest voids tell us about the initial conditions in the early universe? Could voids this large have implications for modifications to our cosmological models? These questions continue to motivate research, even as the basic picture of the void has been well established. One interesting development has been the recognition that voids themselves have internal structure. Early conceptions often treated voids as simply empty spheres, but detailed observations have revealed that voids have complex shapes with internal variations in density. Some regions within the Boötes Void are more empty than others. There are filaments and sheets of slightly higher density gas within the void, invisible to direct observation but detectable through their effects on background light. This internal structure provides additional information about how voids form and evolve. Researchers have also explored whether the void's existence has any implications for fundamental physics beyond standard cosmology. Could the void tell us something about the nature of gravity on the larger scales? Could it provide evidence for or against various theories of modified gravity that attempt to explain cosmic acceleration without dark energy. So far, the evidence suggests that the void is well explained within standard general relativity and the standard cosmological model. But these questions remain active areas of research. Looking forward, the next generation of astronomical surveys and instruments promised us to refine our understanding of the Boötes Void even further. The Vera C. Rubin Observatory, the Square Kilometre Array Radio Telescope and other planned instruments will map cosmic structure with unprecedented precision. When these instruments examine the Boötes region, they will likely discover more of the faint galaxies and gas clouds within the void, and they will measure the void's properties with greater accuracy than ever before. There's also growing interest in understanding how voids like the Boötes Void fit into the broader cosmic web, how they connect to surrounding structures, and how they influence the evolution of nearby galaxy clusters and superclusters. The void doesn't exist in isolation. It's part of a complex network of structures. And understanding these connections might reveal new insights into large-scale cosmic dynamics. And so we find ourselves more than 40 years after the void's discovery with a reasonably clear understanding of what it is and how it formed, but also with new questions that continue to emerge as our observational capabilities improve and our theoretical understanding deepens. The Boötes Void remains a subject of active research, a remarkable cosmic structure that continues to teach us about the universe's nature and evolution. Let's turn now to consider the void's place in human imagination and culture, the ways in which this vast cosmic emptiness has captured our attention beyond purely scientific interest. There's something about vast emptiness that speaks to the human imagination in ways that fullness sometimes doesn't. Throughout history, people have been drawn to deserts, to oceans, to empty skies, finding in these spaces both terror and transcendence. The Boötes Void, though far more vast and remote than any earthly emptiness, taps into this same deep human response to the experience of nothing, the confrontation with absence and scale. When news of the void's discovery reached beyond the scientific community in the early 1980s, it captured public attention in ways that many astronomical discoveries don't. Popular science articles described it as the Great Nothing, the largest hole in the universe, a cosmic mystery that challenged our understanding of reality. There was something viscerally striking about the idea that such a vast region of space could contain almost nothing. That emptiness on this scale was possible. Some of the early public reactions carried an element of unease or even fear. The void was sometimes portrayed in sensational terms, as a threat or an anomaly that didn't belong in an orderly universe. Headlines occasionally implied that the void's existence was somehow alarming, that it represented a flaw in the cosmic fabric. This reaction reveals something interesting about human psychology. We're uncomfortable with emptiness, with absence, with the idea that vast regions of reality might contain nothing of significance. But there's another, more contemplative response to the void that has emerged over the decades, particularly among those who've taken the time to understand what it actually represents. This response sees the void not as threatening but as profound, a reminder of the universe's scale and our own smallness within it. The void becomes a source of perspective, a way of understanding just how vast reality is and how rare and precious the concentrations of matter and life might be. Artists and writers have occasionally drawn on the Boötes Void as a subject or metaphor. Science fiction authors have set stories in or near the void, exploring what it might mean for civilizations to exist in such isolation. Poets have used the void as an image of cosmic loneliness, or as a representation of the spaces between things, the absences that define presence. Visual artists have created works inspired by the void's vast darkness, trying to capture the sense of scale and emptiness that numbers alone cannot convey. There's a philosophical dimension to the void as well, one that connects to long-standing questions about being and nothingness, presence and absence. Western philosophy has a rich tradition of thinking about nothing, from Parmenides' assertion that nothing cannot exist to Heidegger's exploration of nothingness, as a fundamental aspect of being. Eastern philosophies, particularly Buddhism and Taoism, have different but equally rich traditions of contemplating emptiness and the void. The Boötes Void offers a concrete physical manifestation of emptiness to contemplate. It's not merely an abstract concept, but an actual region of space-time, vast beyond comprehension, where the usual structures and contents of the universe are largely absent. For some thinkers, this makes the void a perfect subject for meditation on the nature of reality, a reminder that the universe is as much defined by what isn't there as by what is. There's also something democratizing about the void's remoteness. Unlike many astronomical objects that can only be studied by professional astronomers with access to large telescopes, the void is in some sense equally accessible to everyone. None of us can see it directly. None of us can visit it. None of us can experience it except through imagination and abstract understanding. This puts everyone on equal footing, amateur and professional alike, all of us equally distant from this vast cosmic emptiness. For educators and science communicators, 90 minutes. You've been here for 90 minutes, quietly, patiently, choosing this over everything else the world was offering you tonight. Do you know how rare that is? Most people cannot sit with something slow and meaningful for more than a few minutes before reaching for something louder. But not you. Not tonight. This channel exists for exactly this kind of person, and a like and subscribe is how we find more of them. It is how we find each other. Thank you for still being here. Now let's continue. For educators and science communicators, the Boötes Void has proven to be a powerful teaching tool. It helps illustrate concepts about cosmic structure, scale, and evolution in ways that are immediately striking. Students who might find discussions of galaxy clusters or dark matter somewhat abstract often respond viscerally to the idea of a region 330 million light-years across that contains almost nothing. The void makes the cosmic web structure tangible in a way that describing filaments and clusters alone sometimes doesn't. There's also a curious emotional quality to contemplating the void, something that people often report when they first truly grasp its scale and nature. It's a mixture of awe and melancholy, wonder and loneliness, excitement and dread. This emotional response is part of what makes the void compelling beyond its scientific interest. It touches something in us, some fundamental response to scale and emptiness that transcends purely intellectual engagement. And perhaps this is appropriate. The universe is not merely a collection of facts to be catalogued, but a reality to be experienced and felt, even if that experience comes through imagination rather than direct observation. The Boötes Void reminds us that the cosmos contains wonders that are as much about absence as presence, that emptiness itself can be remarkable, that understanding reality means grappling with the spaces between things as much as with the things themselves. Let's consider now how the void fits into our broader efforts to understand the universe's structure and evolution, and what it reveals about the processes that have shaped the cosmos over billions of years. One of the most remarkable things about the universe is that it has structure at all. When we observe the cosmic microwave background radiation, the afterglow of the Big Bang that comes to us from when the universe was only 380,000 years old, we see a remarkably uniform distribution of matter and energy. The temperature variations across the CMB are only about 1 part in 100,000, tiny fluctuations on top of a nearly perfect uniformity. Yet today, more than 13 billion years later, the universe is highly structured. Galaxies cluster into groups and superclusters. Vast filaments of galaxies span hundreds of millions of light-years, and enormous voids like the Boötes Void contain almost no galaxies at all. How did we get from near-perfect uniformity to such dramatic structure? This question is one of the central concerns of modern cosmology, and voids are an essential part of the answer. The key insight is that gravity amplifies differences. Those tiny fluctuations in the early universe, differences in density of only 1 part in 100,000, were enough for gravity to latch onto. In regions that were slightly more dense than average, gravity was slightly stronger, pulling in more matter from surrounding regions. This made those regions even denser, which made their gravity even stronger, which pulled in even more matter. Over millions and billions of years, this gravitational feedback loop turned tiny initial fluctuations into the dramatic structures we see today. But this process doesn't just create overdense regions, it also creates underdense regions, because the matter flowing toward overdense areas has to come from somewhere. Voids are the necessary counterpart to the overdense regions. The overdense regions are the necessary counterpart to the underdense regions. The overdense regions are the necessary counterpart to the underdense regions. The overdense regions are the necessary counterpart to the underdense regions. The overdense regions are the necessary counterpart to the underdense regions. The overdense regions are the necessary counterpart to the underdense regions. The overdense regions are the necessary counterpart to the underdense regions. The overdense regions are the necessary counterpart to the underdense regions. The overdense regions are the necessary counterpart to the underdense regions. The overdense regions are the necessary counterpart to the underdense regions. The overdense regions are the necessary counterpart to the underdense regions. The overdense regions are the necessary counterpart to the underdense regions. The overdense regions are the necessary counterpart to the underdense regions. The overdense regions are the necessary counterpart to the underdense regions. The overdense regions are the necessary counterpart to the underdense regions. The overdense regions are the necessary counterpart to the underdense regions. The overdense regions are the necessary counterpart to the underdense regions. The overdense regions are the necessary counterpart to the underdense regions. The overdense regions are the necessary counterpart to the underdense regions. The overdense regions are the necessary counterpart to the underdense regions. The overdense regions are the necessary counterpart to the underdense regions. The overdense regions are the necessary counterpart to the underdense regions. The overdense regions are the necessary counterpart to the underdense regions. The overdense regions are the necessary counterpart to the underdense regions. The overdense regions are the necessary counterpart to the underdense regions. The overdense regions are the necessary counterpart to the underdense regions. The overdense regions are the necessary counterpart to the underdense regions. The overdense regions are the necessary counterpart to the underdense regions. The overdense regions are the necessary counterpart to the underdense regions. The overdense regions are the necessary counterpart to the underdense regions. The overdense regions are the necessary counterpart to the underdense regions. The overdense regions are the necessary counterpart to the underdense regions. The overdense regions are the necessary counterpart to the underdense regions. The overdense regions are the necessary counterpart to the underdense regions. The overdense regions are the necessary counterpart to the underdense regions. The overdense regions are the necessary counterpart to the underdense regions. The overdense regions are the necessary counterpart to the underdense regions. The overdense regions are the necessary counterpart to the underdense regions. The overdense regions are the necessary counterpart to the underdense regions. The overdense regions are the necessary counterpart to the underdense regions. The overdense regions are the necessary counterpart to the underdense regions. The overdense regions are the necessary counterpart to the underdense regions. The voids are the necessary counterpart to the clusters and superclusters, the places matter left behind as it concentrated elsewhere. The Boötes Void in this framework began as a region in the early universe that happened to be slightly less dense than average. Perhaps 1 part in 100,000 less dense, maybe even less than that. But that tiny difference was enough. Over billions of years, as structure formation proceeded, matter flowed out of this region toward denser areas nearby. The void grew and deepened, becoming more and more underdense as the universe aged. Computer simulations of this process are remarkably successful at reproducing the structures we observe. When cosmologists set up a simulation with initial conditions matching what we observe in the cosmic microwave background, and then let the simulation evolve according to the laws of gravity and cosmology, the simulated universe develops clusters, filaments, and voids that look very much like what we see in the real universe. The fact that these simulations naturally produce voids similar to the Boötes Void is strong evidence that we understand the basic processes involved. But there are details that matter. The exact distribution of matter in the early universe determines where structures form and how large they grow. If the initial fluctuations had been slightly different, the Boötes Void might not exist, or it might be larger or smaller, or located somewhere else. In this sense, the void's existence is somewhat contingent, dependent on the particular pattern of density fluctuations that happen to exist in our region of the universe after the Big Bang. This raises an interesting question. In other regions of the universe, far beyond what we can observe, are there voids larger than the Boötes Void? Almost certainly yes. The observable universe is vast, but it's not infinite, and if the universe as a whole is larger than what we can see, which many cosmologists believe, then there's no reason to think the Boötes Void is the largest void that exists. It's simply the largest one we've discovered in our observable patch of the cosmos. Understanding structure formation also helps us appreciate the timescales involved. The universe is currently about 13.8 billion years old. Structure formation has been proceeding throughout most of that time, with the first stars and galaxies forming perhaps a few 100 million years after the Big Bang and structure continuing to evolve up to the present day. The Boötes Void has taken billions of years to reach its current size and emptiness, a slow process of matter evacuation and void expansion that continues even now. In the future, the void will likely continue to grow. As the universe continues to expand and as dark energy's influence becomes increasingly dominant, matter will continue to flow out of voids toward dense regions, and the expansion of space within voids will continue to stretch them larger. Billions of years from now, the Boötes Void might be significantly larger and even emptier than it is today, continuing the trend that began in the early universe. There's something almost poetic about this process, the way the universe transforms itself from near uniformity to rich structure over billions of years. The tiny quantum fluctuations in the first moments after the Big Bang, differences so small they barely registered, have grown into galaxies and voids spanning hundreds of millions of light years. The universe has become more interesting, more diverse, more structured over time, driven by the simple action of gravity amplifying small differences. And voids like the Boötes Void are an essential part of this story. They're not anomalies or accidents, but natural outcomes of structure formation, the dark spaces that must exist for the bright structures to form. Understanding voids means understanding how the universe sculpts itself, how it creates diversity from uniformity, how it builds the cosmic web that stretches across billions of light years. Let's turn our attention now to what the void's existence tells us about the fundamental parameters and properties of the universe, the numbers and values that determine how reality behaves. Every structure in the universe contains information about the fundamental properties and parameters that govern reality. The cosmic microwave background tells us about the universe's composition and age. Galaxy clusters tell us about how matter clumps under gravity. Supernova observations tell us about cosmic acceleration, and voids, including the Boötes Void, tell us things that other structures cannot, providing constraints on cosmological models in unique ways. One of the key parameters in cosmology is the matter density of the universe, usually denoted by the Greek letter omega. This parameter tells us how much matter exists in the universe, relative to a critical density that determines whether the universe is geometrically flat, open, or closed. Observations of voids help constrain this parameter, because the formation and growth of voids depend sensitively on how much matter is available to be distributed unevenly. If the universe had much more matter than we observe, gravity would be stronger, and it would be harder for voids to form and grow. Matter would be more tightly held by gravitational attraction, and the evacuation of underdense regions would proceed more slowly. The existence of large empty voids like the Boötes Void tells us that the matter density can't be too high, because otherwise such voids wouldn't have had time to form in the universe's current age. Conversely, if the universe had much less matter than we observe, voids might be even larger and more common than what we actually see. The distribution of void sizes across the universe provides statistical information about matter density, with the population of large voids being particularly sensitive to this parameter. When cosmologists compare observed void statistics to simulations with different matter densities, they find good agreement when they use the matter density we've measured through other means, about 30% of the critical density. Voids also provide information about the dark energy density and properties. As we discussed earlier, dark energy affects how voids expand over time. By measuring the growth rate of voids at different cosmic epochs, comparing nearby voids to distant voids, astronomers can constrain how dark energy's influence has evolved over cosmic history. This provides an independent check on measurements of dark energy made using other techniques. The shape of voids also carries cosmological information. In a flat universe with particular expansion properties, voids should appear roughly spherical when we account for the redshift space distortions caused by the expansion of the universe. If voids appeared systematically elongated or flattened in particular ways, that would tell us something about the universe's geometry or expansion history. Measurements of void shapes, including the Boötes Void shape, have been used to perform what's called the Alcock-Paczynski test, which constrains the expansion history independently of other methods. Another important parameter is the primordial power spectrum, which describes the distribution of density fluctuations in the very early universe. This spectrum, which we can observe directly in the cosmic microwave background, determines what sizes of structures should be most common. Voids provide a way to test whether the power spectrum we infer from the CMB actually produces the right distribution of structures in the later universe. The fact that observed void statistics match predictions based on the CMB power spectrum is a powerful confirmation that our cosmological model is internally consistent. There's also information in the void's internal structure. As we've learned more about the small-scale distribution of matter within voids, including the gas and the few galaxies they contain, we've gained insights into processes like galaxy formation efficiency and gas cooling. The properties of void galaxies constrain models of how galaxies form and evolve in different environments, complementing what we learn from galaxies in denser regions. All of these constraints work together to build up a consistent picture of cosmic parameters. When we combine void statistics with measurements from the cosmic microwave background, galaxy surveys, supernova observations, gravitational lensing, and other techniques, we get a remarkably coherent picture of the universe's composition and properties. The fact that independent methods agree so well is strong evidence that our cosmological model captures something true about reality. The Boötes Void, in this context, is more than just an interesting astronomical object. It's a data point in a vast web of observations that constrain fundamental physics. Its size, its emptiness, its shape, its evolutionary history, all of these properties contribute to our understanding of how the universe works on the larger scales. Each new measurement of the void refines our knowledge of cosmic parameters, helping to narrow the range of possible values and rule out models that don't match observations. This is one of the beautiful aspects of modern cosmology. No single observation proves or disproves a theory, but the accumulation of many different observations, each constraining different aspects of the model, builds up a picture that's robust and well tested. The Boötes Void is one piece of this larger puzzle, but it's an important piece, one that helps ensure our cosmological model works not just for dense regions but for empty ones as well. Looking forward, even more precise measurements of void properties promise to further tighten cosmological constraints. As surveys map more voids across different cosmic epochs, as techniques for measuring void growth rates improve, as simulations become more sophisticated in predicting void properties, our ability to extract cosmological information from voids will continue to advance. And this brings us to consider what future observations might reveal about the Boötes Void and other large voids, what questions might be answered by the next generation of telescopes and surveys. The study of the Boötes Void is far from complete. Each new generation of telescopes and instruments reveals details that previous observations missed. and the next decade promises particularly exciting advances in our ability to map and understand voids. Let's explore some of the questions that future observations might answer and the techniques that will be used to answer them. One of the most straightforward advances will come from deeper galaxy surveys. The Vera C. Rubin Observatory, scheduled to begin full operations in the mid-2020s, will observe the sky repeatedly in unprecedented detail, cataloguing billions of galaxies, including many faint dwarf galaxies that current surveys miss. When this survey examines the Boötes region, it will almost certainly discover more galaxies within the void, refining our census of what exists there. Each additional galaxy discovered helps us understand the void's properties more precisely and tests our models of structure formation. Radio surveys using facilities like the Square Kilometre Array will map the distribution of neutral hydrogen gas throughout the universe, including in voids. This will provide a more complete picture of the void's matter content, revealing gas that's too cold and diffuse to form stars, but that still contributes to the overall mass. Understanding the gas distribution in voids helps constrain models of how gas cools and collapses to form galaxies, and why this process is so inefficient in underdense regions. Gravitational lensing surveys will also improve dramatically in coming years. As more distant galaxies are observed and their shapes measured precisely, weak lensing maps of the void region will become more detailed and more sensitive. This will allow better measurements of the total mass in the void, including dark matter, and will help determine whether there are any significant concentrations of dark matter that don't have associated visible galaxies. One particularly exciting possibility involves using the void to study dark energy more precisely. Future surveys will measure the positions and redshifts of millions of galaxies in and around voids, allowing precise measurements of how voids are expanding over time. By comparing the expansion rate within voids to the expansion rate in denser regions, astronomers can test whether dark energy's influence varies with environment. Any detected variation would have profound implications for understanding dark energy's nature. There's also growing interest in using voids to test modified gravity theories. Some physicists have proposed alternatives to dark energy in which gravity behaves differently on very large scales than general relativity predicts. These modified gravity theories make specific predictions about how voids should behave differently from what standard cosmology predicts. Precise measurements of void properties could potentially distinguish between dark energy and modified gravity explanations for cosmic acceleration. The cosmic microwave background will continue to provide information about voids through studies of the integrated Sachs-Wolf effect. Future CMB observations will map the temperature fluctuations caused by photons passing through voids with greater precision, providing independent measurements of void gravitational potentials. Combining these measurements with direct observations of void galaxies will provide powerful tests of our cosmological model. Future observations might also reveal whether there's any unusual physics operating within voids. While current evidence suggests that voids are well explained by standard cosmology, it's always possible that more precise observations will reveal anomalies or unexpected phenomena. Perhaps there are types of dark matter that preferentially accumulate in voids. Perhaps there are exotic particles or fields that only reveal themselves in the universe's emptiest regions. Science advances through both confirmation and surprise, and keeping an open mind to unexpected discoveries is essential. There's also the possibility of using voids for fundamental physics experiments. Some researchers have proposed that the emptiness of voids makes them ideal locations for detecting extremely weak signals that would be swamped by foreground sources in denser regions. For example, certain signatures of primordial gravitational waves might be more detectable when looking through voids than when looking through regions full of intervening galaxies. Computational advances will allow more detailed simulations of void formation and evolution. Next-generation cosmological simulations will model the physics of galaxy formation, gas dynamics, and dark matter in unprecedented detail. These simulations will make more precise predictions about what we should observe in voids, allowing more stringent tests of our models when compared to observations. As our observational capabilities improve, we might also discover voids that are even larger than the Boötes Void. The observable universe is vast, and while we've surveyed large portions of it, there are still regions that haven't been mapped in detail. Each new survey has the potential to reveal structures that previous surveys missed, including potentially record-breaking voids that would further test our understanding of structure formation. One question that future observations might help answer is whether the Boötes Void is actively influencing its surrounding structures. Do galaxy clusters near the void's edges show any unusual properties? Are there systematic motions of galaxies away from the void toward denser regions? Are there signatures of cosmic flows that trace back to the void's gravitational influence? These questions require precise measurements of galaxy velocities and positions over large regions, but future surveys will provide exactly this kind of data. There's also interest in using machine learning and artificial intelligence to analyse void properties and search for patterns that humans might miss. By training algorithms on large data sets of simulated voids and then applying them to observed voids, researchers might discover new correlations or relationships that provide additional cosmological constraints. This is an emerging area of research that promises to extract maximum information from increasingly large data sets. And perhaps most fundamentally, future observations will continue to refine our understanding of what voids truly are and how they fit into the cosmic web's evolution. Each new measurement adds to our knowledge, each new technique provides a different perspective, each new discovery either confirms our models or challenges them in productive ways. The study of the Boötes Void is not a closed chapter, but an ongoing story, one that will continue to unfold as our capabilities advance. Let's consider now the broader philosophical implications of the void's existence, what it means to contemplate such vast emptiness, and what that contemplation reveals about our relationship with the cosmos. There's a particular quality to late-night thoughts about the cosmos, a kind of philosophical vertigo that comes from truly contemplating the scale and nature of the universe, and few cosmic phenomena inspire this feeling quite like the Boötes Void. 330 million light-years of nearly empty space, a volume so vast that it contains only a tiny fraction of the matter we would expect, challenges us to think about existence and absence in ways that everyday experience never requires. What does it mean for such a vast region to be empty? We're familiar with emptiness on human scales. An empty room is one without people or furniture. An empty container is one without contents. But the void isn't empty in this simple sense. It contains space itself, that mysterious substrate in which events occur and through which light travels. It contains time, flowing forward as it does everywhere else. It contains fields, gravitational and electromagnetic and quantum, woven through every point in that enormous volume. And it contains some matter, dark and visible, however sparse, so perhaps quote 4 isn't quite the right word. The void is better described as sparse, underpopulated, deficient in the structures and concentrations that characterize most of the universe we observe. But this semantic distinction doesn't diminish the void's power to inspire wonder. Even a sparsely populated void, containing perhaps 60 small galaxies across a volume that should contain thousands, represents an extraordinary divergence from the cosmic average. From one perspective, the void is a reminder of how much of reality is defined by absence. We tend to focus on what exists, on the positive content of the universe, galaxies, stars, planets, life. But the universe is overwhelmingly characterized by what doesn't exist in most places. Vast stretches of space contain no stars, no galaxies, no planetary systems, no life. The concentrations of matter that we find so interesting are rare exceptions to a cosmic norm of emptiness. This can feel alienating, or it can feel liberating, depending on your perspective. The alienating view sees the void as evidence of cosmic indifference, a reminder that the universe doesn't organize itself for our benefit or with our existence in mind. Most of reality is hostile or at best indifferent to life as we know it. The void is simply a particularly dramatic example of this larger truth. But there's another way to see it. The liberating view recognizes that the rarity of structure makes it more precious, more remarkable. Galaxies form not because they must, but because particular conditions allowed them to. Life exists not as a cosmic inevitability, but as a contingent outcome of specific circumstances. The fact that most of the universe is void makes the parts that aren't void more significant, not less. We exist in an exceptional place, and that exceptionalism is part of what gives our existence meaning. The void also invites contemplation of different kinds of existence. We think of existence primarily in terms of things, objects, entities with boundaries and properties. A galaxy exists, a star exists, a person exists. But what about regions of space? Does the void exist in the same way that a galaxy exists? It certainly occupies space and time. It has properties, size, shape, density, gravitational influence. Events can occur within it. Photons cross through it. In what sense, then, does the void exist? These questions might seem purely philosophical, disconnected from scientific concerns, but they touch on deep issues about the nature of reality that science itself grapples with. Quantum field theory, for example, tells us that what we think of as empty space is actually a seething quantum foam of virtual particles and fields. Even the emptiest void is, at the quantum level, far from empty. It's filled with quantum fluctuations, virtual particle-antiparticle pairs appearing and annihilating, zero-point energy permeating every cubic centimetre. This quantum perspective adds another layer to contemplating the void. At the larger scales, the Boötes Void appears almost empty, a vast darkness punctuated by occasional small galaxies. But zoom in far enough, down to the quantum level, and that apparent emptiness reveals itself as rich with activity, with the constant churn of quantum processes that fill all of space. The void is simultaneously empty and full, depending on the scale at which you examine it. There's also a temporal dimension to consummating the void. It has existed for billions of years, and will continue to exist for billions more, likely growing larger and emptier as the universe ages. From a human perspective, these timescales are incomprehensible. The void has existed for longer than Earth has existed, longer than the sun has existed. Civilizations could rise and fall, species could evolve and go extinct, and the void would remain, essentially unchanged, a stable feature of cosmic structure. This permanence can be comforting or disturbing. Comforting because it suggests a kind of cosmic stability, structures that persist far beyond the ephemeral concerns of human life. Disturbing because it highlights how brief and fragile our existence is compared to the timescales on which the universe operates. The void doesn't know we exist and wouldn't care if it could. It simply is, vast and dark and patient, a feature of reality that will outlast everything we build and everything we are. Yet for all its vastness and indifference, the void is part of the same reality that includes us. The same physical laws that govern the void's formation and evolution govern the chemistry of life. The same primordial fluctuations that seeded the void's underdensity also seeded the overdensities that became galaxies like our Milky Way. We and the void are both products of the same cosmic processes, different outcomes of the same fundamental physics playing out across different regions of space. This connection is worth pondering. We're not separate from the void or from the cosmic web it's part of. We're embedded in that same structure, located in one of its denser regions, built from matter that participated in the same gravitational dance that created both clusters and voids. Understanding the void means understanding the processes that created the conditions for our existence. The void is not alien to us, but rather part of our cosmic context, part of the larger story of which we're a small chapter. And perhaps that's the deepest lesson the void offers, that significance and scale are not the same thing. The void is vastly larger than Earth, larger than the solar system, larger than our entire galaxy, but it's not more important, not more meaningful. Meaning is not a function of size. A human life, brief and tiny by cosmic standards, can contain as much richness and significance as billions of light years of empty space. Perhaps more, because meaning requires consciousness to recognize it, and consciousness, as far as we know, is rare in this universe of ours. Let us carry these thoughts forward as we approach the final movements of our exploration, where we'll consider what it all means and where the story of the Boötes Void might lead us in the future. There is a peculiar beauty in absence, in the spaces between things, in what remains unsaid or unseen, and the universe itself seems to understand this aesthetic principle through structures like the Boötes Void. Vast regions where the typical fabric of cosmic structure simply fades away into a darkness more profound than what we encounter when we look up at the night sky from Earth, because even our darkest nights are filled with the light of stars from our own galaxy, while the void knows a darkness that few places in the universe can match. Artists throughout human history have understood that negative space is as important as positive space, that what a painting doesn't show can be as meaningful as what it does show, that the pauses in music can be as expressive as the notes themselves, and the universe, in its own way, seems to practice this same aesthetic, creating a cosmic web that is defined as much by its voids as by its filaments and clusters, a grand composition in which silence and sound, darkness and light, absence and presence all play essential roles in creating the whole. We might even think of the void as a kind of cosmic meditation space, a region where the universe sits with itself in quiet contemplation, where the frenetic activity of galaxy clusters and the violent drama of cosmic collisions gives way to profound calm, where time passes slowly and little changes except the gradual expansion of space itself, stretching the void ever larger, deepening the silence, making the darkness just a bit more complete with each passing billion years. This is not to anthropomorphize the void, to suggest that it has consciousness or intention, but rather to recognize that we find in it qualities that resonate with human experiences of peace and simplicity, that when we contemplate the void we're drawn to use language typically reserved for meditation retreats or wilderness sanctuaries, places where one goes to find quiet and stillness and perspective, and perhaps that's what the void offers us on a cosmic scale. A place that exists more in imagination than in any possibility of visitation, but that nonetheless provides a mental sanctuary, a space for thoughts to expand and settle. The void reminds us that the universe contains multitudes, not just in the sense of diverse structures and phenomena, but in the sense of diverse modes of being, places where activity dominates, and places where stillness prevails, regions bright with newly forming stars and regions dark with ancient emptiness, zones of complexity and zones of simplicity, and that all of these modes are equally valid, equally part of what the universe is, equally deserving of our attention and contemplation. And so we find ourselves, deep into this journey now, with our understanding of the void expanding to include not just its scientific properties, but its aesthetic and philosophical dimensions, recognizing that this vast region of space is simultaneously a fact to be measured and a phenomenon to be experienced through imagination, both a challenge to our cosmological models and an invitation to contemplate the deeper patterns and meanings that organize reality. The study of structures like the Boötes Void cultivates a particular kind of humility, a recognition of how limited our perspective is and how vast the universe remains beyond our ability to fully comprehend it. And this humility is not a weakness, but rather a strength, an honest acknowledgement of our position in the cosmic order that allows us to ask better questions and hold our conclusions more lightly, more openly to revision when new evidence emerges. Consider what it means to measure a structure 330 million light-years across, to map its boundaries and catalogue its contents and calculate its properties, all from a single vantage point on a small planet orbiting an ordinary star in one galaxy among billions, because that's what astronomers have done with the Boötes Void, built up an understanding of this enormous structure using photons that travelled across cosmic distances to reach our telescopes, each photon carrying information encoded in its wavelength and intensity and direction of travel. The fact that this is even possible, that we can learn anything at all about such a remote and vast structure, is itself remarkable and worthy of appreciation, because there's no particular reason the universe had to be intelligible to creatures like us, no cosmic law that required reality to organise itself in ways we could potentially understand, and yet it does. The universe follows patterns that our minds can grasp, obeys laws that our mathematics can describe, reveals its secrets to patient observation and careful reasoning. We don't know with certainty what the void will look like in billions of years, though we can make educated guesses based on our models of cosmic evolution and dark energy, because those models might be wrong or incomplete in ways we haven't yet discovered, and the universe might hold surprises for us even on the largest scales and longest timescales, developments that no current theory predicts and that will require new physics to understand. This uncertainty, this acknowledgement of the limits of our knowledge, is central to scientific humility, but it's a humility that coexists with confidence in what we do know, because science advances not by claiming absolute certainty, but by building up increasingly robust and well-tested models of reality. Models that work extremely well within their domains of applicability, even if they might eventually be superseded by more comprehensive theories. We can be confident that the Boötes Void exists, that it's genuinely underdense in galaxies and matter, that it formed through gravitational processes acting on initial density fluctuations, that it contains some dark matter and a small number of galaxies. All of these claims are supported by extensive evidence and are unlikely to be overturned. But we should also remain humble about the possibility that there are aspects of the void we haven't yet discovered or understood. There's also a humility that comes from contemplating the void's indifference to human concerns and human existence, because the void doesn't know or care that we're studying it, doesn't organise itself for our convenience or understanding, simply exists according to the laws of physics without regard for observers. And this indifference is not cruel or hostile, but simply a fact of reality, a reminder that the universe is larger than us and older than us, and will continue long after we're gone. This cosmic indifference might seem depressing from one angle, but from another it's liberating, because it means we're free to find our own meaning and purpose, not constrained by some cosmic plan or universal significance, free to create value and meaning through our choices and relationships and endeavours, to build islands of warmth and connection and understanding in a universe that provides the raw materials but leaves the architecture to us. And perhaps this is the deepest form of humility, recognizing that our significance is not given to us by the universe, but rather created by us within it, that we matter not because we're at the center of cosmic attention, but because we choose to matter to each other, to care for each other, to build communities and pursue knowledge and create beauty. All of this happening on a small scale against a backdrop of cosmic vastness that knows nothing of our efforts, but that provides the stage on which our small dramas unfold. The Boötes Void, in its vast darkness, reminds us of this relationship between the small and the large, the significant and the insignificant, showing us that size and importance are not the same thing, that a human life can contain more meaning than billions of light years of empty space, not because the universe grants that meaning, but because consciousness creates it, because minds capable of contemplating the void are themselves more remarkable than the void they contemplate. One of the most profound insights of modern physics is that the universe is interconnected across all scales, from the smallest quantum fluctuations to the largest cosmic structures, and the Boötes Void, despite being a region characterized by absence and emptiness, participates in these connections just as fully as denser regions do, because the processes that created the void operated at multiple scales simultaneously. linking the quantum realm to the cosmic web in ways that reveal the deep unity underlying physical reality. On the larger scales, the void is part of the cosmic web itself, occupying a specific position in the three-dimensional network of clusters, filaments, and voids that spans the observable universe, connected to other voids and to denser regions through this overarching structure, participating in the evolution of the web as it grows and changes over cosmic time. These connections across scales reveal something profound about the nature of physical law, that the same fundamental principles operate everywhere, at every scale, creating a coherent universe rather than a disconnected collection of phenomena, and the void, for all its emptiness, exemplifies this coherence as clearly as any galaxy cluster does. There's also a more abstract kind of connection to consider, the way that understanding any part of the universe helps us understand other parts, because the physics we learn by studying galaxy formation in voids applies to galaxy formation in other environments. The cosmological parameters we constrain using void statistics help us interpret observations of distant supernova or the cosmic microwave background. And the mathematical tools we develop to simulate void formation can be applied to other problems in computational cosmology. This interconnection of knowledge mirrors the interconnection of physical reality. Both are characterized by deep relationships where apparently separate phenomena turn out to be linked through common principles and shared origins, where understanding one thing illuminates many things, where the universe reveals itself to be not a random collection of unrelated facts, but an integrated whole governed by elegant and universal laws. The void also connects us, as observers and questioners, to the broader cosmos, because in studying the void, we're exercising the same capacities of reason and observation that we use to understand anything else, demonstrating that human minds, products of billions of years of cosmic evolution, have developed the ability to comprehend structures vastly larger than themselves, to reason about processes operating on timescales billions of times longer than human lifetimes, to connect the very small to the very large through chains of logic and evidence. This is itself a kind of cosmic connection, consciousness arising from matter and then turning back to understand the matter from which it arose, minds that are made of atoms contemplating the distribution of atoms across hundreds of millions of light years, thoughts that are patterns of neural activity grasping the patterns of cosmic structure, subjectivity emerging somehow from objective physical processes, and then achieving objective knowledge about those processes. And perhaps this is the deepest connection of all, the one that makes our exploration of the Boötes Void meaningful on a personal level, the recognition that we're not separate from the cosmos but part of it, that the atoms in our bodies were forged in stars and dispersed through space and eventually gathered into planets and organisms, that we are made of the same substance as galaxies and voids, that we participate in the same cosmic story that includes the Boötes Void's formation and evolution, connected across all scales from quantum to cosmic in an unbroken chain of physical and historical relationship. There is a curious parallel between the vast spaces of the cosmos and the intimate spaces of consciousness. Both contain depths that seem inexhaustible. Both resist complete mapping or final understanding. Both inspire a kind of awe when we contemplate them honestly. And as we approach the end of our journey through the Boötes Void, it seems worth reflecting on how our exploration of outer space might relate to our experience of inner space, how contemplating cosmic emptiness might illuminate the nature of mind and awareness. The void's vastness, 330 million light-years of near emptiness, exceeds our ability to truly imagine it. We can state the numbers and understand them mathematically. We can create visualizations and models. But the actual experiential reality of such vastness remains beyond our grasp. And this limitation is not a failure of our minds, but rather a reflection of the fact that we evolved to navigate much smaller spaces, to comprehend distances we could walk and scales we could manipulate with our hands. There's also something to be said about the quality of attention that both astronomical observation and inner observation require. Both demand patience and sustained focus, the willingness to sit with uncertainty and incomplete information, the ability to notice subtle details against a background of darkness or silence, and both reward this attention with discoveries that deepen our understanding, revealing structures and patterns we wouldn't have noticed with more casual observation. The vastness of the cosmos and the vastness of consciousness also share the quality of being inexhaustible. No matter how much we learn about the universe, there's always more to discover, and no matter how deeply we explore our own awareness, there's always greater depth available. And this inexhaustibility is not frustrating, but rather wonderful, ensuring that there will always be new territories to explore, new questions to ask, new understanding to develop. And perhaps this is part of what draws us to contemplating structures like the Boötes Void late at night, when the external world quiets down and we're left alone with our thoughts, because in these moments the parallel between outer and inner becomes more apparent. We feel our own consciousness as a kind of space within which experiences arise and pass away, and we recognise in the cosmic void something that resonates with our own inner experience of spaciousness and emptiness. This is not to claim any mystical connection between the Boötes Void and human consciousness, but rather to recognise that we bring our full humanity to scientific contemplation, that when we study the universe we do so not as disembodied intellects but as conscious beings with inner lives, and that the patterns and qualities we observe in the cosmos sometimes resonate with patterns and qualities we observe in ourselves. The void, then, becomes not just an object of study, but a companion in our exploration of existence, a fellow traveller in the mystery of being, and as we contemplate its vast darkness, we're also contemplating the vast spaces within ourselves, the depths of awareness that contain our thoughts and perceptions, the background silence within which our inner life unfolds, and in this parallel contemplation we might find a kind of peace, a recognition that both inner and outer infinities are part of what we are and what we're part of. As we near the end of our long journey through the Boötes Void, having explored its discovery and its properties, its formation and its future, its scientific significance and its philosophical resonance, we return finally to where all good science begins and ends. With wonder, that peculiar mixture of curiosity and humility that drives us to ask questions while acknowledging how much we don't know, that keeps us seeking understanding while remaining open to surprise and mystery. The void embodies this wonder perfectly, because even after decades of study we cannot claim to fully understand it. We know much more than we did when Kirshner first discovered it. In 1981, we've mapped its boundaries more precisely, catalogued more of its galaxies, measured its properties with greater accuracy. But there remain questions we cannot answer, and mysteries we cannot solve, aspects of the void that resist our attempts at complete explanation. And this is good. This is how it should be, because science is not about eliminating mystery but about deepening it, about replacing superficial questions with more profound ones, moving from quote 5 to quote 6 to quote 7 to quote 8, each level of understanding revealing new depths of complexity and new horizons of ignorance beyond what we currently know. The void teaches us to be comfortable with not knowing everything, to hold our theories lightly even as we test them rigorously, to remain open to the possibility that the universe might surprise us, that our models might be incomplete in important ways, that there might be phenomena we haven't yet imagined waiting to be discovered in the darkness between the galaxies. The few galaxies within the void become more remarkable when we understand how isolated they are, how they formed in a region where galaxy formation should have been suppressed, how they've evolved in quiet solitude for billions of years, each one a testament to the fact that even in the most unlikely environments, under the most difficult circumstances, structure and light can still Before I say goodnight, I need you to know something. When this video was posted, most people scrolled right past it. They saw the length, they saw the topic, and they kept scrolling. But you didn't. You stayed for 2.5 hours, you chose depth over speed and wonder over noise, and I think that says something beautiful about the kind of person you are. If this channel has given you something tonight, a little more peace, a little more wonder, a little more understanding of the world you live in, then a like and subscribe is the kindest thing you can leave behind before you sleep. Not just for this channel, but for the next person out there tonight who needs exactly what you just found here. Now, rest. You have earned it. Structure and light can still emerge from darkness. The void's vast emptiness becomes more meaningful when we understand that it's not truly empty, that it contains dark matter and quantum fields and the subtle influence of dark energy, that photons from distant galaxies cross through it carrying information about the universe's structure and evolution, that it participates in cosmic processes even though it contains so little visible matter. And the void's future becomes more poignant when we understand that it will likely grow even larger and emptier as the universe ages, that it represents perhaps a preview of what most of space will eventually become, that in billions of years the universe might consist primarily of voids with matter concentrated into increasingly rare and isolated clusters, showing us that emptiness might be not just a temporary state, but the cosmos's ultimate destiny. These understandings don't resolve all mysteries or answer all questions. They simply give us better questions to ask, more informed perspectives from which to contemplate the universe, and that's exactly what good science should do. Not eliminate wonder, but focus it. Not replace mystery with certainty, but replace shallow mystery with deep mystery. Surface puzzles with fundamental questions about the nature of reality itself. The Boötes Void, then, is both an answer and a question. It's the answer to the question, __quote_9__, but it's also a question about how structure forms and evolves, about what dark matter and dark energy are doing in that vast space, about whether there are phenomena occurring there that we haven't yet detected or imagined, about what it might be like to exist in such isolation. And as we carry this sense of wonder forward, as we prepare to let this particular journey come to rest, we can appreciate that the void has given us something valuable, not just knowledge or understanding, but also perspective, a sense of the universe's scale and complexity, a reminder of how much we don't know and how exciting that not knowing can be, an invitation to continue asking questions and seeking understanding while remaining humble and open to surprise. The wonder we feel contemplating the void is the same wonder that drives all scientific inquiry. That makes us look up at the night sky and ask, quote, 10, quote, that makes us peer through microscopes asking, quote, 11, quote, that makes us develop theories and run experiments and build instruments to extend our senses and our reasoning beyond their natural limits. All in service of that fundamental human impulse to understand the reality we find ourselves part of. And so, we come to understand that the Boötes Void's greatest gift might not be the specific facts it teaches us, but rather the wonder it inspires, the sense of possibility and mystery it maintains, the reminder that the universe is vast and strange and more remarkable than we can fully comprehend, and that this incomprehensibility is not a failure, but rather an invitation. An endless source of questions to explore and mysteries to contemplate, stretching out before us like the void itself, vast and dark and full of possibility. And so we've travelled together for these past 2.5 hours, from the initial discovery of the Boötes Void through explorations of its properties and formation, from discussions of dark matter and dark energy, to contemplations of meaning and consciousness, from the largest scales of cosmic structure down to quantum fluctuations and back again, covering 330 million light-years of space and 13 billion years of time, all from the comfort of wherever you are right now. Thank you for staying with me through this long journey into the void and back, for lending me your attention and your imagination, for being willing to contemplate vast scales and deep questions late into the night when perhaps you should have been sleeping, but chose instead to explore the cosmos. And I hope this time together has given you something valuable. whether that's new knowledge about the universe or simply a peaceful few hours before sleep. We began by asking what the Boötes Void is, and how something so vast and empty could exist in our universe, and we've arrived at answers that are both satisfying and incomplete. We know the void is real, formed through natural processes from quantum fluctuations in the early universe, amplified by billions of years of gravitational evolution, containing some matter, but far less than typical regions of space, expanding and evolving according to the same laws that govern everything else. And yet we also know there's much more to learn, questions still to answer, mysteries still waiting in that vast darkness. Perhaps the truest answer to what the void is would be this. It's a reminder of the universe's vastness and variety, a demonstration that reality contains not just the bright concentrations of matter we call galaxies, but also the dark expanses between them, not just activity and complexity, but also stillness and simplicity, not just what is present, but also what is absent, and that all of these are equally part of what the cosmos is, equally deserving of our attention and wonder. I hope, wherever you are in the world right now, that you're comfortable, that your breathing has slowed and deepened over the course of our journey, that your thoughts have quieted or at least taken on a gentler quality, that your body feels heavy and warm and ready for sleep, that the concerns and tensions of the day have faded into the background, replaced by a sense of vastness and perspective that comes from contemplating the universe on its own enormous scales. Look up at the sky tomorrow night if you can, if weather and light pollution permit, and remember that what you're seeing is just the nearest stars in our own small galaxy, that beyond them lie billions of other galaxies scattered across billions of light years, organised into a cosmic web of clusters and filaments and voids, and that one of those voids, invisible to any instrument humans have built but real nonetheless, spans 330 million light years and contains only a handful of small galaxies lost in that enormous darkness. Think of those galaxies, if you will, those few scattered islands of light in the Boötes Void, each one containing billions of stars, some of those stars perhaps hosting planets, some of those planets perhaps harbouring life, all of it existing in profound isolation. The nearest neighbours tens of millions of light years away, forever unreachable, forever separate, and yet still connected through the gravitational web and the shared history of cosmic evolution, and the simple fact of existing in the same universe, governed by the same laws. And think of us here, not in a void, but in a rich region of cosmic structure, surrounded by thousands of galaxies within a few 100 million light years, part of a supercluster, connected to the larger web, blessed with neighbours and structure, and all the complexity that comes from existing in a cosmically crowded neighbourhood, and how that's neither better nor worse than existing in a void, but simply different, another way for matter and energy to organise themselves, another expression of the universe's infinite creativity. In the end, what we're left with is not certainty, but understanding laced with mystery, not answers but better questions, not the elimination of wonder but its deepening and enrichment, and that seems like the right place to arrive as we prepare for sleep, in that space between knowing and not knowing, between day and night, between waking and dreaming, where consciousness begins to dissolve into something simpler and the boundaries we normally maintain start to soften and blur. The void exists. A vast and dark and mostly empty, a hole in space 330 million light years across, and that's remarkable, and you exist, conscious and aware and contemplating that hole from billions of light years away, and that's equally remarkable, and both are part of the same cosmic story, the same grand evolution from quantum fluctuations to galaxies and minds, from simplicity to complexity to consciousness, all of it connected. All of it part of the same elegant tapestry of existence. Sleep well tonight, knowing that you're part of something larger than yourself, something vast and ancient and ongoing, the cosmic story that includes galaxies and voids and everything in between, that includes you and everyone you love and everyone who's ever existed. All of us made of stardust and carried forward on the expansion of space, all of us participants in this grand experiment of existence. This remarkable fact that the universe is here and we are here to contemplate it. Dream, if you dream, of vast dark spaces and distant lights, of galaxies separated by emptiness and yet connected by gravity and history, of time stretching back billions of years and forward into an unimaginable future, of consciousness arising from matter and contemplating the matter from which it arose, of all the beauty and strangeness and profound mystery that characterizes the reality we find ourselves part of. Good night.